So this short video is a little bit different to the previous ones because it contains a parameter n in the integrand, and what I would like you to do is to look at this integral with pen and paper and try to explore for which values of n you are able to calculate the integral. And then after you've had a go at it, you can come back and we'll discuss the solutions and comments and the integrals that you can't do so easily on the next couple of slides. So I will see you in a minute after you've had a go. Welcome back. Let's go on to the next slide. So what we want to do now is to look at our class of integrals where we have this parameter n. And one of the first values you might think of looking at is n is 0, and x to the 0 is 1, so that gives us this integral. And the next is n is 1, x to the 1 is x, and that gives us this integral. So on this slide, I just want to look at these two, compare and contrast, and on the next slide, I think we're going to see what the general structure is. So if n is 0, what we're going to have is the following. So n is 0, we have the integral of cosine of x squared with respect to x. This is not an integral we can do by inspection. It's not an integral that we know. So what we would tend to do, I think, is to make a substitution because of the argument here making it difficult. So I'm going to say that my new variable u is equal to x squared, and that means that du dx is equal to 2x. And the key formula that I'm thinking about trying to use is, of course, our friend, that the integral of f of u of x, a function of x, if that function is multiplied by du dx and then integrated with respect to x, this is equivalent to f of u integrated with respect to u, and then at the end we can replace u by u of x. So that's the key formula that we are thinking about using. So let's recall that and have that at the tip of our fingers for the rest of this video. So what do we have? Well, this tells us that the integral of the cosine of x squared with respect to x is going to be, now we don't have a 2x in the integrand here, but what we can do is we can put it in by hand as a factor of 1. So I'm going to insert here. So we're going to write the cosine of x squared, and then I'm going to write 1 over 2x times 2x integrated with respect to x. And that means that we have the integral of the cosine of x squared over 2x, and then this is multiplied by du dx integrated with respect to dx, so that's that. So effectively in a moment we're going to be able to replace that by integrating with respect to u. So what we have is the integral of the cosine of u, because x squared here is u, that's why we made that choice. And on the bottom, we have 1 over 2x, so we can just take the half outside. But we've still got a 1 over x, and so what we're going to have to do on the bottom is replace that x by u, or rather, because u is x squared here, I'm going to say that x is the square root of u. And here I'm assuming x is positive. If x is negative, we'd need to be careful with the minus sign. But let's assume for simplicity x is positive. And this is now integrated with respect to u. And I don't know about you, but that looks like a horrible integral. And in fact, it can be proven that this integral cannot be calculated or expressed in terms of functions such as polynomials, exponentials, trigonometric functions, logarithms, the functions which we call the elementary functions. So this integral, the integral for n is naught, cannot be calculated in such terms. So I'm just going to put a cross against it and say we can't do that one. What about n is 1? Well, here we're on a much happier ground, and so let's look at that. So if n is 1, what we have is the integral of x times the cosine of x squared integrated with respect to x. And now, when we look at this, what we see is that we have outside of the cosine the derivative of our new variable u with respect to x. So essentially, if we even don't think about defining u, what we see is that this is the derivative of that. And by inspection, we can just write the answer down. So I'm going to just leave a space, and I'm going to say it's going to be something like the sine of x squared, because the derivative of sine is cosine. And then when we think about differentiating this, we would get the cosine of x squared, which we need in this integrand. And then from the chain rule, if you differentiate this, you get the cosine of x squared times the derivative of the argument, which is 2x. And here we have an x. We don't want 2x. So all we have to do is to put a factor of a half in front and add an integration constant. So this integral is actually really, really easy if n is 1. And so I think we can definitely be rather happier about this integral. So n is 1, we're very happy, and we can perform the integral by inspection. So let's try and summarize what we've seen on this slide. So we have this class of integrals. If n is naught, we couldn't do it. And the real reason is that we were looking from this formula to have the derivative of the argument of the cosine out front. And we didn't have it. And we can insert a 1 and try to put it in by hand, but it generates a very difficult integral. In this case, n is 1. In the same way, we have du dx, we have the derivative of this argument here in front. So with practice, you can just look at an integral like that and go, I can write it down in the answer. Leave a space and write out what the numbers are that fix things in a moment. So let's see now how that generates, or how that generalizes to other values of n on the next slide. So we're trying to look at this class of integrals, and we've seen for two values of n that it can be very hard and it can be very easy. We're able to do it using our favorite method of integration, inspection. What about n is 2? Well, if n is 2, it looks very natural, but with a little bit of practice, we start to think this is not going to end well, because we don't have the factor of du dx. Remember that we are going to be trying to do this by a substitution. We're going to say that u is x squared, and that means that du dx, that's the derivative factor that we need to use the formula, is 2x, and 2's we can always sort out, but the x factor is not so obvious. Okay, so you might say, well, hang on, we've got x's here, and let's just have a look at what happens if we try to use one of them. So what I'm going to do is I'm going to peel off one of the x's from the x squared factor. The cosine, of course, we can't change, it is what it is. And then I'm going to put an x here and integrate with respect to x. And I'm going to put in here by hand a factor of 2, and out front I'll put in a factor of a half. So the half and the 2 would cancel, and you see that all we've done is insert a factor of 1. So that's fine. This is du dx. So that means that our integral is equal to 1/2, and it's the integral. Now let's assume x is positive for simplicity. So that's then going to be the square root of u times the cosine of u integrated now with respect to u, because this factor here is the du dx that we need for our key formula. So again, this does not look nice, and I'm going to just say this is not going to be something we can do in terms of the elementary functions. So what about n is 3? Well, if n is 3, again, life is good, because we have, for n is 3, the integral of x cubed times the cosine of x squared integrated with respect to x, and that's going to be the integral of x squared times the cosine of x squared. I'm going to peel off an x, integrate with respect to x. So all I've done is I've just split off 1x from the x cubed and put it here. And I'm going to put in a factor of 2 there and a half here. And now we recognise that this fits into our formula. And what we have here is du dx. So this integral is going to be 1/2 the integral u times the cosine of u integrated with respect to u, and so therefore this is going to be fine, but we are going to need parts. If we continue this, n equals 4 is going to be hard. N equals 5 is going to be doable. But the integral for n equals 5, the integral of x to the 5th times the cosine of x squared with respect to x, using our variable u is x squared, is going to be 1/2 the integral u squared times the cosine of u integrated with respect to u, and that is indeed doable, but we are going to need to use parts, integration by parts, twice. So n equals 6, I hope you agree, is going to be a very hard integral. N equals 7, we're going to need to use parts 3 times, etc. So on the final slide, what I'm going to do is just talk a little bit about the integral for n equals 0, just a tiny bit of an introduction to such things. But just to summarize what we've discussed in this slide, what we've seen is as you change n, it's sometimes easy for n is 1, and for n is 3, it was doable, but you need to use parts once. For n is 5, it's doable and you need to use parts twice. N is 7, parts 3 times, etc. And the real reason that it is sometimes easy is that our integrand here, for example, contains a factor of x that we can write as du dx, and what we are left with here is a factor of u. It can be written in terms of u in such a way that we can integrate it quite systematically. Okay, and with that we'll go on to the last slide. Okay, so first of all, if you would like to practice a little bit more what we've just done, what you could do is you could replace the x squared in the argument of the cosine by, let's say, x cubed, and ask yourself for which values of n can this be easily calculated. And on the next slide, I'm just going to list what those values are. I'm not going to give you any great details. But perhaps it's interesting to discuss also what is the integral of the cosine of x squared and how is it handled. So if you use something like, say, Wolfram alpha, you will find this is the result it states. So this is just a number. And capital C here is a function called the Fresnel C integral. Fresnel was a great French scientist who made huge contributions to optics. And this here is plus an integration constant. This is a lowercase c, it's totally different to this. And the Fresnel C integral is defined in this way. So it's a function of x, and this is an integral over a variable that I'm choosing here to call t. But in a definite integral does not depend on the variable that you're integrating over. But this integral will depend on the limit, which is here x. So you can see, for example, that as you change x, this is going to be changing. You can see immediately, I hope, that if x is naught, c of naught, that will be 0 because you're integrating from 0 to 0, so there is no width in your definite integral, and you're integrating over something cosine of t between at naught, which is finite. So this integral is going to vanish, so that function will vanish when x is naught, and other values can be estimated numerically. And in mathematics, there are very many functions which are defined in this way. And this is something that you will meet more as your mathematical expertise grows. So let's just look now quickly on the next slide at the next practice example. And here are the answers for you for the values of n for which this integral is either trivially easy or at least doable. And with that, I will stop this video.